Hello, hello everyone. We are from Group 12, and our topic would be about production of methane. Our group consists of four people, which is me, and you can see the three others other than me. So we are going to present about production of methane. Thank you. Good afternoon, everyone. Our project centers on the industrial scale production of biomethane via anaerobic digestion. The biochemical engine behind this process relies on highly specialized slow-growing metagenic archaea. It is critical to note that these microorganisms are obligate anaerobes, meaning the presence of even trace oxygen is toxic and will completely kill the culture. For our feedstock, we are targeting the organic fraction of municipal solid waste. These choices turn a costly municipal liability into a high yield renewable energy asset. To make this biology commercially viable, we design an airtight heavy duty engineering vessel capable of handling high solid mixing. Let's look at the physical dimension on the next slide. For section 2.0, we tackle the core physical sizing of our continuous tank reactor (STR) instead of arbitrarily picking numbers. We reverse the engineering workflow based on established literature for municipal waste digester. We establish a baseline target working volume of 750 cubic meter of active organic slurry. Following our Unimap lecture guidance, we implemented a strict 75% liquid to 25% gas headspace ratio. This mathematically locked our total reactor volume at 1000 cubic meter. By applying a standard 2 to 1 aspect ratio, we calculated our final tank dimension and internal diameter of 8.4 meter and total vessel height of 17.2 meters. Next, we configured the internal hydraulic because our tank height is double its diameter. A single mixer would cause massive vertical dead zones and let solid drop to the bottom. Therefore, we designed a single central vertical shaft hosting two distinct set of impellers scaled perfectly at one third of the tank diameter, which is around 2.87 meter. The configuration is highly specialized for methane slurry. The low impeller is an axial flow hydrofoil placed 2.87 meters off the floor to continuously lift heavy organic solid and eliminate bottom dead zones. The upper impeller is the radiant flow Rushton turbine, positioned near the top wheel interface to break up floating scum and maximize mass transfer. To completely eliminate fluid vortexing and ensure true blending rather than just to swirling, we integrated six vertical wall baffles, each exactly 0.86 meter wide. Finally, let's address gas handling and material. Because oxygen is lethal to our culture, traditional air sparging is completely omitted. Instead, we design a biogas recirculation loop. A compressor draw a portion of the gas from our 250 cubic meter headspace and re-inject it through a spranger ring at the absolute bottom of the tank. This provides dual benefit pneumatic agitation to help suspend solid and vapor steering to recover methane efficiently. To maintain biological stability, the system is wrapped in a heating jacket set to mesophilic 37 degrees Celsius because hydrogen sulfide and volatile fatty acid make the environment highly corrosive. All internal and the shell are specified as 316L, which is 316 liter stainless steel to prevent pitting and ensure plant longevity. This physically blueprint is fully detailed in our section 2.7 schematic diagram, also giving an automation team a flawless foundation to build out the PNID, which is on the next section, which my teammate will cover next. Thank you.
All right, now let's move on to our heart of our biological system, the workhouse of our bioreactor, which is the media formulation plan, according to the microbes of our choice. So the microbe of our choice is using Methanothermobacter marburgensis. So this is a thermophilic hydrotropic methogen. In simple terms, it is a hard living organism that consumes hydrogen and carbon dioxide to produce methane. It is optimal growth temperature is around 65 degrees Celsius, which is significantly higher than a typical mesophilic bacteria. This thermophilic nature is a major advantage, as we saw in the Sabatier reaction. Uh, the conversion of CO2 combined with four molecules of hydrogen will end up with the production of methane and two molecules of water. The higher temperature accelerate the reaction kinetics, which means faster methane production, and it also as a natural deterrent, reducing the risk of contamination from others, less heat tolerance microbes. This organism is truly an ideal candidate for a large-scale biological methanation. Now, before we can produce a methane at a scale, we need a grow healthy and active seed culture. This slide shows the formulation for our seed culture medium, which is based on the well-established of DSMZ medium 119. The medium provides all essential nutrients, which is inorganic salt like ammonium sulfate and potassium phosphate for nitrogen and phosphorus, as well as trace of elements and vitamins that is crucial for the archaea metabolism. A component here is inclusion of reducing agent like L-citrine and sodium sulfite. These are critical to maintain the strict oxygen-free anaerobic environment that our organism demands for a survival. The seed culture is grown under a specific gas mixture of 80% of hydrogen and 20% of carbon dioxide at a pressure of 2 to 3 bars. We harvest the culture at mid-expositional phase, which is when the cell is most active and ready to be transferred as an in column for the main production reactor. Okay, as for the main production process, we scale up with this optimized sulfate-based medium. The key components are similar to seed culture, but you'll notice we made a critical choice by using sulfate-based salt instead of chlorides. We have ammonium sulfate as nitrogen sources, potassium phosphate for buffering, and sodium bicarbonate for carbon and alkalinity. We also include a tailored trace element and vitamin solution. Just like in the seed culture, maintaining anaerobic conditions is paramount. So we use an L-crystalline and sodium sulfite as our reducing agent. The choice of sulfate is deliberate and crucial one, and I'll elaborate on it in the moment. With our production media prepared, we need to carefully control the operating condition to maximize methane yield. We maintain the pH at a stable of 6.8 to 7, which is optimal for our organism. The temperature is held at 65 degrees Celsius, and we designed the reactor for a sterile in a place at 121 degrees Celsius for cleaning between batches. A key difference here is the operating pressure. During the seed phase, we use 2 to 3 bars for the production, and then we increase the pressure to between 5 and 10 bars. This is strategy decision according to Henry's law. Increasing the pressure enhance the solubility of gaseous substrates, hydrogen and CO2 in liquid medium. This makes them more bioavailable to the microorganism. We also maintain sparging rate of zero point 0.5 to 1 uh, to an agitation at 200 to 400 RPM using our dual impeller system to ensure the gas is uniformly distributed and constant contact with microbes. So why are we focused on the sulfate-based medium? The answer is in the data. So this slide presents a compelling justification of our primary source material shown in striding 98.5 percent increase in volumetric productivity when using the sulfate medium compared to a traditional chloride-based one. The maintained evolution rate or MER are nearly double, reaching 285.86 meter per mole per liter per hour with sulfate versus 144 with chloride. This isn't just about raw production, true. It is also longevity. At elevated temperature and pressure, we're using chloride ions are highly corrosive and can cause pitting in the 316-liter stainless steel of our reactor. By switching to the sulfate salt, we also protect our critical equipment from this corrosion while simultaneously achieving massive boost in productivity. So it's a win-win. The combination of our mechanism, optimized medium, and control condition leads to impressive performance. As the graph shown, the theoretical methane yield is significant around 143 liters of methane per hour for our reactor size of at standard temperature and pressure. However, as I mentioned earlier, operating at a high pressure is a key factor on achieving this. It is drastically improved gas to liquid mass transfer, ensuring the hydrogen and carbon dioxide are quickly dissolved and available for the microbes. Finally, let's look on why our trace element solution is so specific. This element might be needed in a small amount, but they are absolutely critical for enzymatic machinery of membranesis. As you can see, each metal has specific roles. Nickel is the cofactor for the terminal enzyme methyl coenzyme M radicursate, which actually carries out the final step of methane formation. Iron is essential for electron transfer. Cobalt, molybdenum, tungsten, and selenium are all vitals for other key enzymes in metagenesis pathway. Our optimized sulfate-based trace element solution is formulated to provide the right concentration of these micronutrients. This precise balance ensure all the all these enzymatic reactions run at full capacity, which directly correlates to a high biomass density, which we see with an optical density of 6.79, and our record-breaking methane evolution rate of 285 86 mmol per liter per hour. So thank you. Will be proceeding on to the next slide.
Alright, so today I will present about process monitoring and control. Now, in these sessions, it shows the feed preparation before the reactor. Methylbacterium slurry is pumped into the reactor using a pump, and the hydrogen and the carbon dioxide are separately flowed into the feed tank V101. Now, these gases will be control its composition before entering the reactor. Then, the mixed gases will compresses to increase the pressure and passes through the heat exchanger E101 to heat the gases to maintain the suitable pressure and temperature for Methylbacterium culture to live. Next, in the reactor operations where the inside of reactor, the hydrogen reacts with the carbon dioxide in the presence of Methylbacterium to produce methane and water. And the reactor is also controlled with the temperature, pressure, and safety instrument to protect the reactor if there is abnormal operating conditions. The influence then passes through cooler E102 before entering distillation column T101. In that distillation column, the water is separate from the mixture and the overhead gas flow to carbon dioxide separator T102, where the carbon dioxide will be removed in the area. The methane and hydrogen gases is pumped by pump P102 to the membrane separator M101 for purification, and pure methane is then sent to the product storage. Finally, the recycle system. This is where the carbon dioxide is produced from condenser and hydrogen gas, where it's separate from membrane separator that combine flow together with the carbon dioxide pipeline, which then directly flow all the way back to the feed tank V101. And at the same time, the water is released from the T101 and released as a treat water. Now, this recycle system is to increase methane yield, minimize waste, and improve the overall efficiency of the biological methanation process. And that's all from me. Thank you.
Here I'm gonna present my part about the contamination risk and sterilization protocol for our biomethane production system. To begin, let's analyze the critical contamination risk within our process. Our system utilizes the specialized culture Methanothermobacteria marburgensis, which is an obligate anaerobe. This means that even trace amount of ambient oxygen presents a catastrophic risk, as oxygen exposure permanently destroys by the key catalytic enzyme required for methane production. Furthermore, biological contamination from invading microbes, such as estrogen or sulfate-reducing bacteria, pose a severe threat. If these alien species enter the bioreactor through high-risk interface like the agitator shaft seals, sampling pods or gas purger, they will aggressively compete with our culture for the hydrogen and carbon dioxide gas feedstock. This leads to the formation of tough biofilm and accumulation of volatile fatty acid, which ultimately collapse our methane purity and batch yield. To completely mitigate this risk, we have designed an automated dual-stage cleaning protocol that reads the internal environment without needing to physically dismantle the gas-tight machinery seals. First, we initiate the clean-in-place cycle. This begins with a hot alkaline wash using 1 to 2% sodium hydroxide at 80 degrees Celsius to break down and dissolve organic grime and cellular fats. This is followed by acidic rinse using 1% nitric acid to neutralize chemical residue and completely strip away stubborn inorganic mineral scaling from the internal baffle and impellers. Second, we immediately execute the steam in place cycle. High pressure saturated steam is injected directly into the vessel and piping lines, holding a uniform core sterilization temperature of 121 degrees Celsius for 20 minutes. This step is vital to ensure that heat-resistant bacterial endospores are completely eliminated, even in hard-to-reach piping depth zone. Finally, our choice of media and nutrient handling is critical to safeguarding both of the culture and the mechanical hardware. Standard methanogen media contain high concentration of chloride ions, which cause severe pitting corrosion and stress cracking along stainless steel vessel under hot steam condition. To prevent structural damage, we utilize an advanced sulfide-based medium which eliminates corrosion risk while successfully doubling our overall methane yields. While the core inorganic nutrients are sterilized directly inside the tank during the steam cycle, the vital organic vitamins and reducing agent are heat labile and will be destroyed by the extreme heats. To preserve their biochemical activity, these sensitive components undergo cold sterile filtration through 0.22 micrometer membrane filter. They are then anoxically pumped into pre-cooled vessel under positive gas pressure, establishing the strictly oxygen-free environment needed before inoculation. That concludes my part of presentation. Thank you very much.